So in this video, we're going to be talking about the Carnot cycle. The Carnot cycle is the most efficient cycle in thermodynamics, which operates between two constant temperature reservoirs, namely the high temperature reservoir and the low temperature reservoir. The Carnot cycle is basically operated in four processes, which include two isentropic processes or two adiabatic processes and two isothermal processes. Now let's take a look at the function of each of these components or each of these equipments on the cycle. We have the heater. The function of the heater is to introduce heat into the working fluid through the support of the high temperature reservoir. We have the expander. The function of the expander is to remove work from the system or remove work from the working fluid. We have the cooler. The function of the cooler is to remove heat from the working fluid and send it into the low temperature reservoir. And finally, the function of the compressor is to compress the fluid or add work into the fluid or add work into the system and then return it back to the cooler so that the cycle can continue. Now, I mentioned that there are four processes that govern the Carnot cycle itself. The first process is isentropic heat supply to the system through the high temperature reservoir. That can be seen from here. So you see Q1, heat input into the system through the high temperature reservoir. The second process is reversible adiabatic process, in which work is produced from the system as the working fluid passes through the expander. So that can be seen from here, from state 2 to state 3. As the working fluid passes through the expander, work is produced. The third process is reversible isothermal process, in which heat is removed from the system. So as can be seen, heat is removed completely from the working fluid and sent to the low temperature reservoir. And the final process is adiabatic, work done on the system as the fluid returns back to the initial pressure or returns back to the initial state. Now, this is a TS diagram that illustrates these processes. State 1, from state 1 to state 2 is the heat supply from the reservoir, high temperature reservoir into the working fluid. From state 2 to state 3 is the work removal process from the expander. From state 3 to state 4 is the heat removal process in the cooler. And from state 4 to state 1 is the work addition process or the compression process in the compressor back to the initial stage. Now, observing this TS diagram, this is our saturated liquid lines and this is our gas line or the saturated vapor line. The center is simply called the mixed vapor or the saturated vapor and liquid line. Now, understanding of this TS diagram can help you understand all the formulas you need for your calculation in Carnot cycle, and I'm going to break them down in simple terms for you to understand. Now, calculations in Carnot cycle are done using the enthalpies. Calculations in Carnot cycle are done using the enthalpies. Okay, so the enthalpy at state 1 is simply labeled, since this is completely liquid line, you call that H1, and H1 here is simply what? HF. F there indicates fluid, because at this point the working fluid is on the saturated liquid line, so everything here is completely liquid or completely fluid. On the gas line, that's at state 2, our enthalpy there is H2, and H2 here is equal to Hg. So Hg simply means the enthalpy at the gas or the vapor line. So this can be found in your steam tables. Now, in between here, observe that at state 3 is actually at the saturated vapor and liquid. That is a mixture of both vapor and liquid. So which means there is a need to find what is called the dryness fraction at this point. So dryness fraction at this point is labeled X3. So we need to find the dryness fraction at this point before we can be able to compute the enthalpy at that point. Meanwhile, the enthalpy at that point is H3, and it is given simply as HF3 plus X3 multiplied by HFG3. That's the equation, okay, to find the enthalpy at state 3. Same thing happens at state 4. State 4 is also between the saturated liquid and vapor line, right? So which means there is a need to find dryness fraction at this point, x4. So with the dryness fraction, we cannot be able to compute or find the enthalpy at that point, which is H4, and H4 is equal to, once again, it's going to be HF4 plus X4 HFG4. So HF4 gives us the enthalpy at the fluid region at the given pressure. So you have pressure 1. This pressure 1 governs state 1 and state 2. Pressure 2 governs state 3 and state 4. Now pressure 1, with the value of pressure 1, you simply go to your steam table. You can now find HF. HF there at pressure 1 gives us our H1. And Hg at pressure 1 gives us our H2. Okay, now once it enters into this saturated liquid and vapor line, which is state 3 and state 4, there is now a need to find what? The dryness fraction at state 3 and the dryness fraction at state 4, because with that you can be able to find the enthalpies at each of those states. Okay, another thing to keep in mind from that CS diagram is, if you observe, if I draw a line here, let me draw a dotted line down, you see that this line touches this is the entropy line. CS, this is the entropy line X. So this line touches the entropy line. Observe that state 2 and state 3 are touching the entropy line, so it is the same. Which is why I said earlier that state 2 to state 3 is a reversible adiabatic or isentropy process. That simply means that state 2, the entropy at state 2 is equal to the entropy at state 3. So you simply have S2, okay, to be equal to S3. Remember, it cannot be easy to find S2 simply because S2 becomes Sg, okay? S2 is simply going to be equal to Sg at this given pressure. So when you have your first pressure, you go to the saturated liquid and vapor steam table. At Sg, you can find the value of S2. S2 is simply equal to Sg. Now, S3 itself can now be computed. S3 is going to be equal to still the same formula as this, becomes SF3 plus X3 SFG3. So we use this to find the value of the entropy at state 3. Now state 2 is going to be easy. If you know this pressure, you can simply find S2. Then S3, simply equate the two of them together. This can help you to find your dryness fraction, plug into this equation and find your enthalpy. The same thing, if you now observe, if you trace a line from state 1 to state 4 down, you see that it is touching what? The entropy line. So this also means that state 1 and state 4 are isentropic processes or constant entropy processes, which means the entropy at state 1, S1, is equal to the entropy at state 4. Meanwhile, S1 can be found. S1 is simply equal to what? SF at this given pressure, P1. So the value of SF here equals S1. S1 equals SF at this given first pressure. Now, if you know this, you can now find S4. S4 itself is now going to be equal to still the same relationship. It becomes SF4 plus X4 SG or SFG4. So with this, you equate the two of them together, knowing fully well that you can find S1 if this pressure is known. Now, if you equate the two of them together, you can either find your dryness fraction from there, plug back into this equation and find the enthalpy at state 4. So it's as simple as this. The equations of Carnot cycle are being calculated using the enthalpies. All you need to do is understand the TS diagram and know these little manipulations, then you're good to go. Okay, so to calculate the work done, the heat supplied is between state 1 and state 2. Heat is supplied from state 1 to state 2. So you can still see it there. Heat transferred. What is coming here is completely liquid. What is leaving here now is saturated, right? It becomes a gas, I mean to say. What is leaving here becomes a gas because of the heat supply. So between state 1 to state 2, once again, the enthalpy here is simply, the enthalpy at state 1 is H1, enthalpy at state 2 is H2. Therefore, heat supplied, we call that Q1, is now going to be equal to difference in enthalpy, and that heat must be positive. Whenever a system receives heat or when heat is added to a system, that heat is positive. That heat becomes what? H2 minus H1. So this gives us the heat supplied between or from the high temperature reservoir into the working fluid, H2 minus H1. Now, the enthalpy here is going to be H3. So between state 2 and state 3, expander does work, right? So the work done by the expander, we call that W1, is going to be positive because expander removes work from the system. Anything that removes work from the system becomes positive. When work is removed from the system, that work is positive. So since it's between 2 and 1, it's going to now be H2 minus H3. H2 minus H3 because H2 is always going to be higher than H3. H3 already, this place is becoming liquid. So this enthalpy is going to be lower than H2. So our work added to remove from the system is going to be H2 minus H3. Simple, that's the equation. Similarly, between state 3 and state 4 is the removal of heat in the system. So heat removed, we call that Q2, is now going to be equal to, since it's between state 3 and state 4, heat removal is negative. So obviously state 3 will have a higher enthalpy. Enthalpy at state 4 is labeled as H4. So obviously state 3 will have a higher enthalpy than state 4. But because heat is removed from the system, that heat becomes negative. So it becomes H4 minus H3. So the heat removed from the system is now going to be H4 minus H3. And this heat is going to be negative because H4 is lower than H3. Now, the compressor work is between state 4 and state 1. So that work is labeled W2 here. So W2, which is now work added to the system. Whenever the system receives work or when work is added to the system, that work is negative, right? So work added to the system is now between H4 and H1. So the work done by the compressor becomes H1 minus H4. So it's going to be what? A negative work. It must be a negative work. So also pay attention to the enthalpies. Between state 4 and state 1, the higher enthalpy, the lower enthalpy subtracts the higher enthalpy. So we have H1 minus H4. This gives us the work done by the compressor. So this is how you can know your formulas very easy. So another key question you can be asked in the Carnot cycle is the net work. The net work is simple. It's simply equal to the work done by the expander, which is W1, plus the work done by the compressor, which is W2. So this gives us our net work. So you simply sum these two equations for work done, this and this, you have your net work. Similarly, your net heat supplied, the heat net is simply heat supplied from the high temperature reservoir plus the heat supplied from the low temperature reservoir, and this simply gives us our net heat. Another question you can be asked to find is the specific steam consumption, SSC. Specific steam consumption is simply given as 3,600 kilojoules all over the net work. So this is actually, kilograms per kilowatt hour. That's the unit, kilograms per kilowatt hour. That's the equation. So once you know your network, through this relationship, you can simply compute the specific steam consumption. Alright guys, so I don't think there's another formula I'm leaving out. But if I'm missing any other formula, in the next video when we're going to be solving problem, I'm going to recall those formulas. Alright guys, so I will see you in the next video with an amazing question on Carnot cycle. I'm sure you want to be a part of that video. Do well to smash the subscribe button right now and turn on your bell notification so you don't miss out on that video when it drops. I will see you in the next video. Cheers.